Hi, uh, this is William McCarthy. This project builds a dynamic pricing strategy for ride hailing using reinforcement learning and integer programming and tests how well it generalizes across two data sets. I framed pricing as a Markov decision process. The state captures market conditions, time of day, location, weather, and crucially, the supply level and recent demand. The action is a price multiplier on the base fare from point 0.8 up to 2.0. The reward is revenue on served rides, price times quantity capped by supply, with a small penalty for excessive surging. Because there's no live system to train against, the environment itself is learned from the data. I fit a Poisson demand model and the coefficient on log prices by construction, the price elasticity. That learned model becomes the simulator the agent interacts with. I compute the pricing policy two ways. The first is tabular Q learning, a reinforcement learning agent that learns by trial and error, observing last period's demand and adapting online. The second is integer programming, which plans a whole day of prices in advance to maximize expected revenue, subject to hard business constraints, a cap on average surge for fairness, and a limit on how fast prices can jump. The contrast is the point. The integer program optimizes against expected demand, but can't react once the day starts. The RL agent reacts to what actually happens, but must learn the environment by sampling it. I also compare against three baselines: fixed, random, and a rule-based surge heuristic. On the first dataset, where demand outstrips supply, both optimizers win big. The integer program lifts revenue 54% over fixed pricing. Q-learning lifts it 50%. The rule-based heuristic barely moves the needle. But on the second dataset, the picture completely inverts. Here, supply is abundant, and the best policy is actually to cut prices. The integer program gains just 2%, and Q-learning does worse than doing nothing. Same code, but opposite advice. The reason, it turns out, is structural. Dynamic pricing only has interesting structure when a capacity constraint binds. Without one, constant elasticity demand collapses to a corner solution. This is the policy Q-learning actually learned with no rules encoded. Each cell is the price it chooses. Read it and the economics fall out on their own. When supply is low relative to demand, the top rows, it raises prices to ration scarce capacity. When supply is abundant, it discounts. It rediscovers surge pricing from the revenue signal alone. That's the encouraging result, but the next two slides are where it gets interesting. Here's the first hard finding. Neither dataset can actually identify how demand responds to price. Fit the model naively and elasticity comes out positive in both cases, implying that higher prices raise demand, which is obviously nonsense. The reason is endogeneity. Operators raise prices because demand is already high. Build a simulator on that, and the agent games the artifact for a fake 107% gain. You cannot learn pricing from logged data where price reacted to demand. Second finding. I expected RL to beat the static plan when demand is noisy but predictable. So I swept shock size and persistence, but it never happened. RL never beats integer programming at any setting, and making shocks more persistent made RL worse, not better. A persistent hidden factor turns this into a partially observable problem, and the agent's course state can't track it. One caution. With 3 random seeds, I got the opposite, tidy-looking result. It took 10 seeds to see it reverse. So, Where capacity binds, both methods lift revenue substantially, and the ranking is robust. But the real lessons are the negative ones. Demand identification is the binding constraint, not the algorithm, and RL's adaptivity needs a state that can represent what varies. In future work, what would be good to look at is a richer state with deep RL and proper price experimentation to identify elasticity. Thanks for watching.